evening. Hi. I'm going to present electronic design for Android ThinkSystems on modules. My name is Jinal Dalal. I'm a hardware engineer for Android Things, and I'm really excited to present to you this particular talk, especially because I built hardware for Google for about 10 years, and I built for consumer and enterprise. So everything that you see here are the things that I've learned over the past 10 years, and please don't repeat the same mistakes. All right, let's get started. So before I get into the details of how to build hardware, Android Things has system on module, which is the core component of Android Things, which has CPU, memory, power, as well as Wi-Fi and Bluetooth. This is the core component of Android Things, which allows you to take all the complexity out of your hardware and put the wrapper around it. So going into the detail, this board is about 2 inches by 2 inches, and it basically is something you can buy off the shelf today. So if you were to think of an idea that you want to build using this as the core module, you don't have to go out and design it, and all the technical complexity around this has been taken away from it. As part of this particular talk, the thing that we built internally to Google, in a very simplified way, is this baseboard. This is the board that goes with the SOM and allows you to add more functionality to it. So imagine use cases like cameras, routers, and displays that would like to use the SOM as the core component. It's the baseboard that you end up designing for your solution. It has, in this particular case that I designed, it had a USB ports, audio, HDMI, buttons, LEDs. So this is something you can design. This does not require a whole team of hardware engineers to go out and design it for you. And I'm going to walk you through those steps of how to actually do those things as part of this talk. All right. Before jumping into the details of hardware design again, Android Things joins this group of Android platform, which are about 2 billion devices that exist today, as well as it takes advantage of the Android framework, so it allows you to use what you already know. For example, even in cases of whether it's cars, TVs, watches, and Wear OS, as well as cell phones, you're already familiar with these platforms, and now you're using this to build IoT devices around it. From the ideas perspective and from what this enables, there are a bunch of options to go out and design. In terms of home, you can think about security systems, speakers, routers, doorbells. For enterprise, point of sale, interactive ads, vending machines. I'm going to share some examples of that. And for more of buildings and enterprise buildings, it's cameras, HVAC, smart meters. And for cars and fleet management, you could think about smart parkings, car audios, and so on. The opportunities are endless. There will be about 20 billion devices by 2020. And so this really opens up the whole opportunity. In terms of hardware, how many of you here have actually designed hardware or been part of the design? So having realized a few of them, this is really we are at this point where hardware is really not about is different or hard. It's more about how you actually go through the process to build it. So as much as how software is built, hardware is built differently, but the focus should be really on making those small steps to get you to the right platform and to the more solid hardware. So there are 3 things that have happened in the past, I would say 5 years, that have phenomenally changed the way hardware is built. One, there are 3D printers. If you think about a box or a photo frame or anything that you would like to design, you can actually go print it out today. This, plus the IoT platform that we are building, would enable you to build a platform or a product around it. Secondly, there is crowdsourcing. And third is the cost of manufacturing. All these 3 things have allowed you to experiment with the ideas without actually needing a big team to go out and do it. Again, going back to this example, this, along with the wrapper, took us 1 person at Google to go out and build it. These are just two general examples of what you can do with it, with the existing solutions. For example, a vending machine that doesn't have a display can start using display and phone for its checkout. And with this Android Things platform, you are able to actually experiment with it. As well as the pill dispenser, again, allows you to manage the schedule for the pills, as well as notifications and so on. Again, making something that's been there for a while and making it smart. In terms of, so before we talk about the process again, this is the board that I was just showing you. The red is the baseboard that I designed. The green is the system on module that sits on the baseboard. As you can see, this was for an NXP device, so the SOM is actually an NXP device, but the baseboard is flexible. It allows you to add any features that you would like to use for your product. All right, so process. The first step for hardware design is planning. Planning really means identifying the core components and features that you want, and then sketching it out on paper to figure out how it all connects. Second is prototype. Prototype is about actually buying off-the-shelf hardware and implementing it as an experiment. Third is design. From a software standpoint, design is making the UI. From a hardware standpoint, you're really getting into the nitty-gritty of using the schematic tools, the layout tools, as well as releasing those for manufacturing. And last is qualify. Each of these steps needs to be followed and are really critical for the success of your design, and it needs to be repeated to ensure that you can keep building more volumes. So let's go into the detail for plan. Planning from the hardware standpoint is really one, identifying the components, the features that you want. So you want a USB support, you need a USB connector. If you want audio, you need to add audio connector. If you want to use a display, this again needs to go here. It's critical to actually sketch your design up before you start implementing it. This is a critical step, and you need to think about all the features as well as the rest of the things, which is power and size. So this is in a different dimension. Think about how hot this product is going to get. Where is it going to be used? Is it going to need cables from your product standpoint? Beyond that, also think about the cost very early on so that you don't end up buying components that are expensive from the beginning. And then finally, how is it all powered? Is it a battery powered or AC? This also matters in the design. So that's the planning piece. Next is prototype. I want to emphasize the value of prototype. When you start thinking about your design and you think that you need to wait all the way until you actually design everything in schematic and layout, it's already too late and you already spent thousands of dollars to get there. So before you do that, try and see if you can buy components online, put it on the breadboard, connect wires, and get your basic functionality in place. Again, I'm going to repeat, get your basic functionality in place as much as possible so you know exactly what you are using, how you are using it, how much power does it draw, and even to the extent that how does it look. If you can 3D print something or use a cardboard, it's worth trying it, because by the time you get it to the production, it's going to be too late. Design. This is something where most of the software developers are going to be challenged in terms of how to actually start implementing the schematics. Fortunately, again, in the last few years, there are a lot of open source options that you can use to start sketching out your design. As an example, KiCad is an open source schematic and layout tool that you can use today with no cost and try a simple board. There are a few other options as well from Altium, Cadence, and Eagle, and each one has its own pros and cons. For example, depending on how many layers the board is, or the cost that you're willing to pay for this tool, each one has its own trade-offs. In my particular case, we ended up using Altium, mostly because it's what I knew, and as well as what I was trying to build, which was an 8 to 10 layer board. All right, let's take a little bit deeper into what a schematic really is. So from a hardware standpoint, the schematic is a 2D representation of your design. Every component that you can think about that's going to be on your board needs to be on the schematic. As you can see onto the screen, on the left side is the capacitors that's marked as C1, C2, which are the reference designators. The one in the yellow are generally ASICs or connectors, the components that are tied to these discrete or components. There is ground, which is represented by the lines, which represents the ground of the board. There is a power, which is the input to your circuit. And then all these traces that you see are all your connections. They're physical traces that are going to be populated onto the board to make these connections. Next, after you are finished your schematic, the next step is to start doing the layout. Layout is, in some sense, a 3D representation of what your design is. You start thinking about where the components go physically on the design, how they are routed. Not going into too much detail, but this hardware is tied to physics. And so how you run your single-ended and differential pairs, like clocks and signals, are critical in the design. And this is where you can leverage either some help from online schematic or data sheets, or work with somebody you know. But this is where you need to spend some time thinking about how your board needs to look, where the key components needs to go. This is what the board's layout looked like. And this is just one of the layers. There were 8 layers on this board. The traces or the lines that you see going from top to the bottom are essentially the physical traces that have been routed to a connector. The yellow, I would say, text is reference designators. And if you care about how you're going to debug this board, you need to ensure that these things are placed properly. Similarly, some of the symbols represent where the components needs to go. Once you're done with the layout, the next step is to see what exactly it looks like. And this is pretty cool. In hardware, you can actually start thinking about not only thinking about what you are trying to build, but also feel and kind of see what it is. And this is where things get really exciting. You need to take the time to actually look at where your components are in this framework. For example, are my buttons in the right place? Is LED accessible? Are the connectors accessible for connecting? This is where you can physically check every single thing to make sure that they're lined up properly. For example, one of the issues that we found when we were designing this board is the LED was actually placed in the back. And so it wasn't visually possible to see the LEDs from the front when they are blinking, especially for error LEDs. So it's important, again, to think about these as part of your design. After you're done with this, what happens next is really taken over by the manufacturing company. But what you need to send them is the Gerber files. Now, if you don't know what the Gerber files are a representation or a software text representation of each of these components, the size of the board, the traces, the holes that needs to go onto the board, and as well as all the connections. This is a file that you then send over to your manufacturing company, who then ends up building it for you. It's important for them to not only check this for you, but this is also something that they will help you confirm that they received all the right information. A critical step in this process, even though it might seem simple, it might, in my case, there was an instance where they received the files, but they were corrupted, and they couldn't actually build the right board. So expensive and important step that you need to pay attention to. In terms of manufacturing, there are 2 options today, which is really great in terms of the cost, and there are trade-offs for each one. One is local. once your board is ready, you have your Gerber files, you could release it to somebody locally, either it's US or somewhere else, which generally cost higher, and here are a few examples of which companies you can use. Or you can do it offshore. There, the trade-off is its cost is cheaper, but it also takes much longer time for you to receive your boards. Kind of the key takeaways for manufacturing. One, test every board. It is important that you're building your board for the first time. Do not make the assumption that it's the replica and it's just going to work. You have to test every single board that comes out of the line for the first time. Two, visually inspect before you actually start powering it on. There was an instance where I had the capacitor reversed, and as soon as I plugged in the power, it actually blew, and there was a real fire. So this is real. You got to pay attention to your design. It does matter how careful you are before you actually turn on the power. And third, if possible, don't wait until the boards are shipped to you. Go to the factory if you can, see how, as soon as they come out, and make sure that they work as intended. There have been instances where by the time they reach after 10 to 15 days, you might find a bug. And now it takes another set of changes and time before you can get this error corrected, versus in software, you can just do it in a few seconds. All right, once you have your board, you received it, you checked for key components, whether they have been populated properly or not. The next step is to debug. If you have some basic EE skills, you can use a multimeter to check your signals and see if they are wiggling. You can use a scope if you have one. But really, the key message here is try and debug as much as possible. I'll give you one example here that is not obvious to you, but on the left side, or on the right side for you, the one that is marked as D is a diode. And what we realized as part of our manufacturing process is that the diode was actually reversed. And this diode actually serves a SD card. SD card wasn't detected. Again, visually really hard to see, but this ended up being a bug in our design, where the diode was placed reversed and ended up causing us a no detect for the SD card. Thermals. I'm briefly going to touch on thermals, but this is an important aspect of the hardware design as well. So you would assume that if the hardware works on your table, it's going to work on your desk, it's going to work everywhere else. That's not true. As soon as you start bumping up the temperature on the hardware, you will start seeing all kinds of issues, from shutdown to heating up some components and causing fire. It's important to think about the critical components in your design and make sure you meet the guidelines and the operating spec of those components. If you can detect, in this particular case, I have a heat sink for the CPU. And initially, based on our experiments, we realized that heat sink may not be required. After trying a few experiments on the desk, as well as in a thermal chamber, we realized that this was required to operate the CPU at a particular temperature or range. Again, a small thing in this design, got to pay attention to it. Lastly, mechanicals. After you're done your hardware design and finished the design for it, the next step is what the enclosure looks like. With 3D printing, you can sketch, you can print something out and test it out. Critical here is to look for all the instances where you're going to interact with your design. If there is a button, make sure it's accessible and it's in the place where you want it to be. If it is LEDs, they should be you should be visually able to see them from what is expected out of it. Similarly for connectors, make sure that they're not blocked. It's always worth experimenting and printing something out or use a cardboard to make sure that the EE components are in its place before you go to the next step. In terms of mechanicals, there are two options to actually design this, design it. One is called soft tooling, and the other one is hard tooling. In soft tooling, this is where you use the cost is higher, the turnaround time is again shorter, and it is really designed for limited use cases. So if you expected the lifetime of a product to be 3 years, a part that is soft tool might last only a year. A hard tool is where you actually use the sheet metal and use a hard tooling solution to build your product. This is higher cost. There is a high NRE associated with it, a slower kind of turnaround, used mostly for high volume products, and it's designed for the full life of the product. This is what you buy when you buy consumer electronics. This is most of the tooling is hard tooled, while all the experimental hardware that you have internally or at your desk, for example, might all be soft tooled. Okay, finally, qualify. I think after you've finished all the aspects of this design, you got to qualify your product from end to end in terms of software. So bring the hardware up, run all the software on top of it, and make sure the design is solid and all the features are meeting your expectations. And set up a pass-fail criteria for them so that you know what's going to happen if certain features are turned on and off. This finishes the cycle from plan to qualify. And in some ways, you would think that you are done. Not yet. Take this process that I just showed, and if you are trying to build a product that's going to be thousands of units, you need to move on to the next phase, which is what I'm going to go through. So EVT is the engineering validation test. The whole process that I just showed you needs to be repeated for EVT. Generally, EVT is about tens of units. And the goal here to validate your schematics, your layout, your design, the core features, the components on the board, and ensuring that it all works. It is not necessarily designed to run all the software that is expected at the end product. The cost for EVT is high. So in some ways, you would think that the cost of the product is going to be high. But that's not necessarily true. There are few reasons why the cost for EVT is high. One, it's low volumes. Two, it is manufactured in a very controlled way. So there's a high cost associated from an NRE standpoint. And then three, the components that you buy are also going to be limited. And so that's going to keep your cost high. Next is DVD. DVD is the design validation process where you validate the design and also involve some of the software teams into your platform. This is also where you test out the software bugs, and generally you find the issues which are 10% of the total yields. So pay attention to those, fixing those, and then ensuring that you are ready to move on to the next stage. In terms of the cost for a DVT platform is about a few percent lower than EVT. The cost is, again, driven by the cost of the board, the components that you select, as well as the process that you're using. Finally, PVT is a production validation test. This is generally in thousands of units, and you need to ensure that the manufacturing line that you have is set up to handle the volumes that you are projecting. This validates that process as part of this step. In terms of the issues that you find are the 1%. Imagine now you're building thousands of units, and so you're going to catch those small bugs that happens in your hardware, which you wouldn't have found otherwise. The other focus is really on ensuring that the process and the line is set up to go really high. Cost. The cost for PVD is generally less than half or even 1/3 of what the cost of EVT is. This is really where the high volume kicks in. Along with that, the tooling is going to be hard tooling. So that means that you're going to start using much better design solution for your product. Finally, mass production. Mass production is where you are going to start selling your units to your end customers. This is going to be thousands of units. And this is where you start also qualifying your second sources, where you start adding more new components to your design to reduce cost. And the yields are going to be critical. So pay attention to how your product is performing in the factory, especially for those small percentage of failures that you are seeing. This steps is really where the real cost comes in. This is generally, like I said, less than 1/3 of the cost of an EVT or even lower. And you can further push it by using second source, optimizing your processes, even kind of changing some of the design in terms of the components that you have selected and reducing the cost or even removing them. Finally, you would think you're done. Again, not yet. There is a bunch of tests that are required for you to meet before you can ship out to your customers. And each country has its own set of compliance tests, EMI and EMC tests, which is critical to the product, and of course your software qualification. So let's try to wrap this up. In terms of you did the planning, you did the prototype, you did the design, and then you did the qualify. These 4 steps needs to be repeated in each of these EVT, DVT, PVT, and mass production phases. And each of these steps are designed to de-risk your hardware, as I mentioned earlier. If you take these steps and follow it through, most likely your design will not have the issues that would cost thousands of dollars. That's the end of this talk. There are a bunch of things around. If you haven't checked out the Android Things demo, you can go check it out. There's Code Labs. And there are also a few other presentations from Android Things team that you can check it out. And the scavenger hunt. If you haven't tried this yet, you should try it. You can end up getting a kit. And I would love to get your feedback. Thank you.